So this is the agenda today. Lynn has already introduced, I'll go ahead. So here's the instructions of what you're going to do with your sample. So this is the sample I prepared and I manipulated into this shape as a permanent shape. And then those ones are the temporary shape I defined in hot water and hold it until it cools down. So it fixes in those temporary shape. And every time I put it back in hot water, it all goes back to the permanent shape. So I'll show some videos of this process. This is the first example. So I just deform it and hold the shape I want until it cools down. Takes like 20 seconds maybe. The video is speed up. And once I put back in hot water, it will always goes back. There are two more examples, I think. It's the same sample, so you can define multiple temporary shapes if you want. But the permanent shape is the one you have in your hand, most likely.
Is the permanent shape like brittle? Will we accidentally break it if we have bad performance or more?
Can you ask that question again?
Is the permanent shape like brittle? Will we break it if we bend it too hard at this point?
If you break it, it will.
Yeah, it's brittle.
Brittle, okay.
Yes, so has all the classes, right? It's actually even more brittle than PLA silicone if you ever break it. So that would be careful when it's cold, yeah.
This is the generally the process, and several things to note. You use hot water, so the water is boiling on your table, and try to use a tweezer when you are when you get your sample from the hot water, and be careful with the pointy tweezers. Yeah, after you take it out of the hot water bath, I think you can manipulate it with your hand. So here we can go with the first step, which is to remove the silicone tubing of your sample. I also showed a video. So I think each team has only one blade, so you guys can share. So basically you cut through the silicone tube, but be careful not to cut down your sample and peel it off.
Yeah. How about each team choose the simplest one on the table, right, to start with, and then that person can share some experiences.
Yeah, if you have difficulty in taking off some of your 3D samples, you can ask for help.
This is not something we're gonna do in this lab, but for your final projects, if you figured, hey, this is a good material I want to continue playing with, but it's kind of annoying to always have hot water in the equation of the design context you're thinking. This shows you can actually embed just a magnetic wire or any other, conducting wire. You can heat up with the current. So instead of basically you need to introduce some heat, right? That could be hot water, it could be a hair dryer, or it could be as simple as a conducting wire you travel through your structure. If that makes any sense, feel free to ask questions, and we can maybe just quickly scroll through the video as well.
Yeah, so in this project, they use PLA, which is also a type of chip memory materials. And then it's as basically similar mechanism of the chip memory effect. So you can also embed any kind of heaters with your in your epoxy sample that you are playing with right now. So you can get rid of the hot water bath. You can heat it with a power supply or something to trigger the chip memory effect. So if any of you want to use chip memory materials or chip memory polymer in your final project, you can talk to me. Feel free to talk to me.
And you can imagine using a battery to heat up a resistor, right? That would use heating. That would make it a more practical for practical, more feasible for this.
So what they are showing here is that they only hit this part of the sample. So it's soft and it's chip memory, but the other part is rigid.
And this shows you can also embed the polymer into a fabric sleeve. So say if you like the sheet memory effect, but you don't like the texture or the materiality of it, you could imagine hiding inside the piece of fabric. In this case.
I think there's a question up there.
I was wondering in like nano techniques too, like if there's a curve, like let's say you have something that curls up when this is a certain temperature. I was wondering if it would kind of like snap to that once you hit a threshold, or whether it was like a slow, it curve a little bit as it got warmer, a little bit as it got warmer. I don't know if there's a response.
Yeah, remember, remember last lecture we showed maybe just very briefly a plot. So glass transition temperature as a concept, right? Before the glass transition, for the polymer we're playing with is about 60 degrees. It's always cold. And then beyond that, it's getting warmer. And that does mean there likely a sudden change. It's not going to be gradual. However, Ku's research, her PhD research, is a lot to do with sequential control of multiple sheet memory effect responding to different temperature. In that case, I'm not sure if we're going to talk about it today or not. You do have some conditional controllability.
Yeah, but it's not controlled from the temperature. It's controlled from the composition of the polymer.
Yeah, if you have like this much, it's 60, this much, it's 60.
Yeah, that's true. So now I'm gonna introduce a little bit of a deeper, more information about the working mechanisms of chip memory materials. So first, the category, the chip memory materials can be divided into chip memory alloy and the chip memory polymer. So we haven't got a chance to play with chip memory alloy, but I also briefly introduced it. And the polymer in your hand is a kind of thermoset, chip memory thermoset here. So first I'll briefly introduce what's alloy and polymer. So alloy is a combination of metal with at least one other metal or non-metal. So it can be multiple types of metal putting together, or a metal with another non-metal element. And for polymer, there is a famous analogy of the structure of polymers. So polymer consists of very long molecules, and you can imagine it as a plate of spaghetti. So all the polymer chains are just like the noodles within the spaghetti, and they are entangled together. That's how you can think of polymers, the inner structure of a polymer. So I'll first introduce a little bit of the chip memory alloy. So for the working mechanism for chip memory alloy, it's similar to from the phenomena you observed is similar to the polymer. So at high temperature, it will goes back to the remember shape, just as the epoxy you are playing with. And at high temperature, the chip memory alloy is in austenite state. And if you cool it down, it will go to another crystal structure, which is called martensite. So in martensite state, the shape memory alloy is very malleable. So you can deform it on the room temperature. So that's a difference from, that's a different part from the shape memory polymer. You need to manipulate it when it's hot for polymer, right? But for shape memory alloy, you can deform it and manipulate and hold the shape, hold the temporary shape under room temperature. And then if you heat it up again, it will go back to the austenite state and go back to the remembered shape. So here is an example. If you still remember, I've showed this GIF image from last class. So here is the, let's start from the austenite state. So when the piece of alloy is in hot water, it will goes back to the remembered shape. And if you take it out, cool it down, it's the martensite state. And you can deform it into this from a 6-pointed star to this round shape. And once you put it back in hot water again, it will goes back to the remembered shape or the austenite state. I think that's pretty similar from phenomena as you observed today. And for the shape memory alloys, we usually use in lab or experiments is nickel titanium, and it's very commercially available. People have been using it as an actuator or other functions, but if you want to use it as an actuator or other shape memory elements in your final project, you can also feel free to talk to me to discuss more details. And that's all for the shape memory alloy. So the other category of shape memory materials is the shape memory polymer. And the sample in your hand is one type of the shape memory polymer. So for the mechanism, if you can also still imagine the polymer structure here as a plate of spaghetti. So when you are curing the polymer, you define the permanent shape of this plate of spaghetti. So all the polymer chains are entangled in a certain way. And this is the lowest energy state. So that means all the polymer chains tend to go back to this shape whenever they have enough energy. And the reason why you can deform it into another shape is because when you heat it up, it becomes more flexible, and you hold it into another shape, and now the polymer chain wants to go back, but you hold it, you didn't let it to go back until it cools down. So when it hits cool down, it's like you put something in a fridge. The polymer chains are frozen. They cannot move anymore. So the temper shape is fixed there. And once you put it back in hot water or give it enough heat energy, it can go back. It can move again. So it will go back to the permanent shape. That's basically the mechanism of how shape memory polymer remember this permanent shape. And under the category of shape memory polymer, there are two types of polymers. The first one is thermoplastic. So for plastic, I think you should be very familiar with those materials because like a plastic bag from Giant Eagle is plastic. A plastic film you use to cover your food in the fridge, that's also plastic. So it's very common in your daily life. And the definition for a plastic polymer is that it can be very moldable or pliant, or it can be melted at a high temperature, and it will solidify upon cooling. So basically, if you have been worked with PLA, the example here, polylactic acid, is a very commonly used 3D printing filament. So the basic idea for printing with PLA is to melt it at high temperature and then and then extrude it. It will cool down and form the shape you write. So that use the basic features of a thermoplastic, which is melted at high temperature and solidifies upon cooling. And here, so PLA also shows the shape memory effect. And here, if you look at this figure, when you are extruding the PLA from the extruder, you are write it in a certain way. So you actually stretch the polymer chain along the extruding direction. So it's extruded and cooled down very fast. So this is like the temporary shape. And once you heat it up, it will go back. So it will shrink a little bit. And you can use this as a actuator block for your project or something. Yeah. Another example of thermoplastic is polystyrene. If you have seen or used the shrinky discs before, it's a type of polystyrene, and it's a similar idea. So this piece of shrinky discs has been stretched during the fabrication process, or the piece of shrinky discs you get is already been stretched during processing. So if you heat it up, it will shrink in both width and length. And that's also a shape memory effect. So it's kind of similar, but the polymer we are using today is not a kind of thermoplastic, because if you remember, I said, no matter how high temperature the water bath you use, it's not gonna melt. So it will never be too high. That's the feature of the polymer we're using, which is a type of Summerset. So for Summerset so by definition, it's a polymer that formed by irreversibly hardening of a soft pre-polymer. If you remember last lab, when we are synthesizing the epoxy, at first it's a viscous liquid state, and then after curing it becomes solid. So this process is irreversible. Today, there are also students asking me whether we can reprogram the permanent shape that cure it again to make it another permanent shape. No, it's an irreversible process. You can make multiple temporary shapes, but you can only get one permanent shape, which is defined during the curing process. So if you see the top right image, it shows the comparison of thermoplastic and Summerset. So for thermoplastics, it's like a piece of butter. It can be melted at high temperature, and if you cool it down, it can solidify. And for Summerset, it's like a piece of it's like a pancake. It was solidified, but it's not gonna melt. And the bottom right figure shows the inner structure of a Summerset. So this is also the spaghetti structure of polymer chains. But what's different for Summerset is that there are these black dots within this polymer network, which is called crosslinks. So with this crosslink, the polymer can be the polymer network can be more stable and stronger, so it will not easily melt. And also, I will also mention the triggering temperature of the shape memory effect is related to the crosslink density within the network. So an example of Thermoset is epoxy, which is what we used. And I've mentioned the components are the resin and the curing agent, which we were mixing from last lab. And also it doesn't melt at high temperature. Yeah, the third one I also mentioned, the triggering temperature of shape memory effect is related to crosslink density. So as the students suggested, we can get some sort of sequential motion by combining epoxies with different triggering temperature. And the epoxies with different temperature are obtained from the epoxy with different crosslink density. And the common applications for epoxy in our daily life is paint, coatings, and adhesives. So I'll show 2 more examples of the epoxy that I'm working with in my project. So I just mold instead of using a silicone tubing as a mold, I use another rabbit shape silicone mold and then mold the epoxy into it. So I get this rabbit. The permanent shape is as it shows, and I bend the ear of the rabbit to make the temporary shape. So if I heat it up with a heat gun, the ear goes back to its permanent shape. I'm pretty sure you guys are familiar with this process already. And another example is the one I combine epoxies with different triggering temperature. So basically, I have 2 pieces of epoxy. One is triggered by 60 degrees C water bath. The other one will be triggered by 80 degrees C water bath. So I made it a flower shape, and I programmed the temporary shape as the closed flower shape. So it's like something like this. The outer layer can be triggered at a lower temperature, and the inner layer will be triggered at a higher temperature. So we can see this sequential unfolding of the multi-layer flower here. So the outer layer can be triggered at 60 C. And the inner layer can be triggered at 80 C. So that's one of the methods we can use to get some sequential motion. And so by showing these examples, I want to tell you guys the road we are playing with is just the easiest way we can mold a material in the lab session or in the classroom. We have more possibilities in terms of the form factor, and also we can, and as mentioned, we can embed heaters onto the polymer. We can use heat gun. So hot water bath is not the only a way to get heat for the shape memory to be triggered. So if you guys get the idea, we'll spend the rest of the time for brainstorming and sketching. So I think previously we are under the theme of morphing jewelry. So we use a rod to think about some designs. But now, once you have seen other examples, I think you can think beyond a single line or single rod. You can think about other form factors, other possibilities to design some shape changing interfaces with the shape memory polymers. And if you can you can brainstorm a little bit and try to fill the sentence. Thank you. You've already done this before, and submit some responses at this form. We can look at the form together later. So yeah, at the same time, you can try to sketch out your ideas and also upload to the same link. Is there any questions?